Okay, so today we're going to go ahead and talk about different types of energy. So for the first type of energy I want to talk about is potential energy. So something has potential energy because of its position, and it is always going to be stored energy. So it's the stored energy an object possesses because of its position. Okay, so we'll think of different types of potential energy. So like there is chemical energy is an example. Um, Chemical energy, like atoms and all sorts of things, have potential energy in like the atomic molecules, and then that energy becomes available when the atoms rearrange or position changes. And I also think of like gravitational potential energy. If we change the position of an object, it has the potential to create more kinetic energy or different types of things. So I think of the word potential with a lot of these things. Kinetic energy, we've talked about this year, but kinetic energy again is the energy of motion. And again, our equation for kinetic energy is Ke equals 1/2 mv squared, where Ke we know is kinetic energy, and that's going to be measured in joules, or you could just say capital J. M is going to be mass, and that's going to be measured in kilograms. And V is going to be the velocity, and we'll oftentimes measure that in meters per second. Cool. So now let's talk about energy transfer versus energy transform. So when we think of energy transfer, that is going to be when we pass energy from one object to another. And the transfer of energy is going to be called work. So it is going to be called work anytime we transfer energy. While an energy transformation is going to be when we change one type of energy to another form of energy. So it's like when we change some of the kinetic energy to potential or vice versa. Okay, so now let's go ahead and do a couple equations for different things. So let's see. We're going to first talk about gravitational potential energy. So gravitational potential energy. Cool. So let's say we have some object of mass m, some distance h above the ground. So we're always going to need to, when we do a problem involving gravitational potential energy, define ground level or our like base level. So this is going to be, so I'll say define ground level. And I will say this level is the ground, and this is where the height is 0. So the equation we use for gravitational potential energy is going to be PE equals mgh. Or you will also see U stands for potential. You all have so much potential. So U stands for potential, and G means we're referring to gravitational potential energy. So you will see both of these equations used for gravitational potential energy. And let's go ahead and define a couple things. So we know M is mass, and we'll usually want to measure that in kilograms. Granted, any units of mass is fine, but if we're going to use joules, let's use, kilograms. G, we know, is acceleration due to gravity. Acceleration due to gravity. And we know on Earth, we know G is going to be 10 meters per second squared. H is going to be the height above like the ground or wherever we are, and we're going to want to measure that in meters. And again, G is meters per second squared. And then PE or UG is going to be our gravitational PE. And we will want to measure that in joules, or we can say J for short. Cool. Cool. And we already talked about kinetic energy and gave the equation for that. So let's go ahead and go on to spring potential energy. So spring potential energy. Another name for spring potential energy is going to be elastic potential energy. Just because I think of springs they're stretchy things, they have a lot of elastic in them. So, okay, the equation for spring potential energy is going to be U, again, that stands for potential, S stands for spring, is going to be 1/2 kx squared. So I'm going to go ahead and explain a couple of those things. So let's say we have a spring. Let's say it's like that. Now, and let's say it has a mass on top of it. And nothing's happening to that good old mass. But if we compress that spring down a distance x, here's our mass, and it's compressed down like this, then we know that if we were to let go of this mass, what direction would that mass go? That mass would go upwards. That spring has potential stored in it. So a couple things. K we know is going to be our spring constant. And again, that tells us like the stiffness of an object. So it's going to be the object's stiffness of like the spring. And it is going to be measured in newtons per meter. X is going to be how much the spring is stretched or compressed from equilibrium. And again, another word for how much is something is stretched or compressed from equilibrium is going to be your displacement. And we'll oftentimes want to measure the X in meters. And again, we know US is going to be spring potential energy. Spring potential energy, and we will oftentimes, again, energy, we will measure in joules or capital J. Awesome. Okay, so we're going to go ahead and solve a problem together involving calculating different types of energy that an object has. Okay, so let's look at this problem. So we have a mass of 2.2 kilograms is placed on a stiff vertical spring that has a spring constant of 950 newtons per meter. Okay, so the spring is vertical, so we have our spring like this, and here is that 2.2 kilogram object. Cool. And again, the K of the spring is going to be 950 newton meters. And again, this is a pretty stiff spring. That is a pretty big spring constant. While like in the lab that we did, the springs were around 100 newton per meters or less. Okay, so then the object is then pressed against the spring until it's compressed at a distance of 77 centimeters. So let's go ahead and draw out it is compressed 77 centimeters. And here's our little mass, and that spring is really compressed. And again, this is our 2.2 kilogram mass. Cool. The mass is then released and thrown up into the air. The mass moves 3.5 meters above the point from which it was launched. So let's go ahead and draw it all the way up here. So it is, and again, this is our 2.2 kilogram, and this distance is 3.5 meters. Okay. So let's go ahead and I'm going to encourage you to try all these parts A, B, C, and D yourself, and then log back into the video to check your answers. Okay, so what will be the elastic potential energy in the spring just before the mass is released? Oh, sorry. First thing we do after we draw our picture is let's choose a starting point. So again, I would usually choose, and by a starting point, I mean like where are we going to define that gravitational potential energy to be zero? I usually choose wherever the object is starting, or like where it might end as like my initial height is zero. So this looks like a great initial height where that once the spring has been crushed, blah, 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 it's compressed down. Let's choose that as H equals zero. So the elastic potential energy in the spring just before the mass is released. Okay, so that is going to be, we're looking again at that point all the way down here. So I know my equation for spring potential energy or elastic potential energy is 1/2 kx squared. Okay, so K I know is spring constant. X is how much it's stretched or compressed. It is in centimeters right now. We're going to need to convert that to meters. So 77 centimeters, let's see, over 1. There are 100 centimeters in 1 meter. So this is going to be centimeters cancels, 0.77 meters. Okay, so that's 1/2. K is 950. X is going to be 0.77 squared. I plug it into my handy dandy calculator, and I get 281 joules. Okay, so then let's look at the next thing. What will be its gravitational potential energy when the mass reaches its highest point? Okay, so there we go. UG we know is going to be equal to mgh. So the mass is what? 2.2. G we know is 10. Again, we're always using positive 10 if we're on Earth. The height above its launching point is 3.5. And then we get, when we plug that all in, 77 joules. Okay, cool. So now let's go ahead. So we did A, we did B. Let's go ahead and move on to C. Okay, So for C, what will be the velocity of the mass when it reaches its highest point? So right up here, when it reaches its highest point, we know the velocity is 0 meters per second for a split second. So that's an easy one. Velocity is 0 meters per second. Okay. So what will be the kinetic energy of the mass at its highest point? Ooh, okay. So I know my equation for kinetic energy is 1/2 mv squared. If I go ahead and plug everything in, so mass is what, 2.2, velocity is 0, oh my goodness, I get just 0 joules. So at the highest point, I have 0 joules of kinetic energy. And one thing I think about, if I were to, let's say, look at the beginning point, is it moving when it starts? No. So it has 0 joules of kinetic energy when it starts as well. It's only while it's moving that it will have kinetic energy. Awesome. Thanks for watching.